Okay, we're going to start. Here we go. Let's start now. Ready to start. Okay, so let's just start out with a little example here. All of a sudden, it just stopped working. So I want, here is an accumulation function. Okay, ready to start. Here's an accumulation function. I want to use only the rules the shortcut rules that we've made up so far to find the exact rate of change function for this. So if I'm going to use only the rules that I've got so far, what do I need to do to start here? I really don't know about one thing divided by another. We haven't really talked about that. So so if it's one thing divided by another, we don't really have anything for that. So we need to kind of change the form of this to get it so that the structure of it matches one of the rules that we know. Robert has an idea.
Take the x plus 2 and take that to the -1 power.
Okay, what about this? Is that the same thing? Okay, now what's the structure of that? So maybe for easy ones like that, we don't need to ask the question every time, what's the structure? But we want to get in the habit because we're about to have some really, really complicated, ugly ones, and that's going to be the key to doing those well, is to start by saying, what is the structure of this thing? That's going to determine and govern how I start, or the overall structure of the rate of change function. So what is the structure of 12 times x plus 2 to the -1? Can you recognize what structure that is? Yes, ma'am. Is it chain rule? The overall structure of that? No. What is the structure? Is that a hand back there in the corner? Power rule. Is it power rule? Yes, ma'am. Constant multiple. This is a constant multiple times a function. Constant multiple times a function. And how do we find the rate of change of that? So we're doing RGX is the constant multiple times the rate of change. Okay, so like I said, in the future, you don't really have to do that. You're gonna get so good at these easy ones that it'll just be like falling out of bed, and you won't have to do that. But we're just practicing this idea of what is the structure, because that's going to be super important when these get harder. Okay? So now we're going to take 12 times the rate of change of what's inside. What's the structure of that? What rule will we use for that? It's something to a power, right? But there's something is another function. So it's chain rule, right? So this is chain rule, and the exterior function is power rule. So what are we going to do? We're going to take... So you can do it two ways. You can go inside out or outside in. When we derived the chain rule, we saw that really it's the concept of it is an inside out kind of thing. When x changes a little bit, you get a change of the interior function. So what is that? So what's the rate of change of x plus 2? 1. Times the rate of change of the exterior function with respect to the interior function. And that exterior function is to the -1, so it's going to be times -1 to the, or times to the -2. So that's applying our chain rule, and that would be an inside-out approach, but it would be just as legitimate because multiplication is commutative. You can switch the order in multiplication. You can do outside-in also, meaning you could have done this first, and then multiplied by 1 second. This, though, the inside-out kind of way of doing chain rule follows the concept, right? For a little change in x, you get a change of the interior. For that change of the interior, you get the change of the exterior. Okay, but either way, for these is fine. So what does this turn out to be? It turns out to be -12 over x plus 2 squared. So there's our exact rate of change function. There's our exact rate of change function for the function g of x. And so when we did that, when we just did that problem, we actually learned two things, not just one. So the obvious thing we learned is that the rate of change of g, 12 over x plus 2, is the function negative 12 over x plus 2 squared. But we also learned something else. We also learned that if you come across a open form accumulation function like this, now this, having done this rate of change function, allows us to write this open form accumulation function in closed form. Do you remember this? Do you remember this? So this is, we think of this as the rate of change, right? So the rate of change of g. And so what? So what does this whole expression mean? This whole expression is, tell the person next to you, what does it mean? Not what does it equal, but what does it mean? What is it symbolizing? Tell the person next to you. Okay. Volunteer, somebody new. Volunteer. So we need to know exactly what that thing is symbolizing, what it means. Who can articulate that? Is that a hand? Okay, person. What's that? What net accumulation? Yeah, okay, so it's net accumulation, good. Specifically, what net accumulation is it? Is there another hand in the back? Is there another hand back there? Did I see? No? What net accumulation is it? Yes, ma'am. Okay, of the g function, right? Starting at 3 up to any value x. So it's the rate of, it's the net accumulation for some function g whose rate is this, right? Starting at 3 up to x. So if it's the net accumulation of g from 3 to x, how else could we write it? It's the total change in the function g from 3 to x. Yeah, g. So if it's the total change in g, then we can write it this way. And now we can write the closed form. What is g of x? 12 over x plus 2 minus, what's g of 3? And they all said 12 over 5. So look, we just were able to write this particular open form of accumulation function in a closed form. And this will give us what? The net change in g starting from x equals 3. So if you started from x equals 3 and you accumulated according to g up to x, then you'd get this much accumulation from 3. This is the net accumulation from x equals 3. So every time we find an exact rate of change function, we also gain the ability to write some, or actually many, open form accumulation functions, right? Because we could start from any value a here in a closed form. So as you got it. So that question that I asked you, what is the meaning of this? What is the meaning of this? When you're working your homework, you should be asking yourself that question all the time to every expression you come to. Keep practicing the meanings of expressions, okay? Otherwise, calculus is just all a bunch of symbols that you're pushing around with no meaning, right? And that so So then it's your fault if you're saying, what is it good for? Right? So this is the math student said, what am I going to use this for? Well, if it's just symbols, you're right. But we're really focusing on the fact that these symbols and expressions have a real-world meaning about accumulation and rate of change. So practice that. Every time you come to an expression in your homework, practice that. Questions on this example? Yes, I am. Thank you. I am. Okay. So let's talk some terminology here. Given an exact accumulation function, say g of x, its exact rate of change function is called the derivative. It's called the derivative. Okay? We've been focusing on the language rate of change function because that tells us what it is. So derivative is a little more vague. Okay, but when you hear the term derivative, immediately you think, oh, rate of change function, rate of change function. Okay? So in our example, negative 12 over x plus 2x squared, x plus 2 quantity squared is the exact rate of change function for that function g. And so negative 12 over x plus 2x squared is the derivative of g. Okay? So that function that we found, negative 12 over x plus 2 squared, is the derivative of g. Okay? So there are other notations for the derivative besides the one we've... Here's one. So this also means the rate of change function for g, the derivative. Okay, this is prime notation. This also means the derivative of g, or the rate of change function. Okay, and we know what it is. We know it's our trusted form when h is very small, right? It's our trusted form of the rate of change in y over change in x, when h is very small. All right, you can ignore that. So, okay, so for r sub g of x, for us that means a small value of h. So now we have three notations: r sub g of x, d dx, g of x, and g prime of x. They all mean the exact rate of change function, and we call them the derivative of g. Questions on that? So you'll see them all, and we can use them interchangeably. Use them interchangeably. This one is especially, it's worth noting that this one, that notation, we actually see the kind of the meaning in there, right? Because it's the change in the function value, the dependent variable, per change in x. So that one kind of embodies the meaning of it. This one's the easiest to write, but we lose any visual of the meaning. Okay? And this is the one we've been working with for a while. Any questions? All of them, though, are the rate of change of g with respect to x. Okay? All of them, the rate of change of g with respect to x. Okay, so let's practice some more chain rule problems. You had some for your homework, right? Okay, so here is all chain rule problems. Why? Because they're all some type of composite function. One function plugged into another function. Okay? And I've written the chain rule up there, and I did it, this time I wrote it in outside in form, right? Outside in. You're looking at the rate of change of the whole function with respect to the interior times the rate of change in the interior. Okay? So I want you to take some time and work on these. So over here is the function capital C. And then over here, we're going to make a table out of them, is what? The rate of change of the function capital C, right? Or the derivative of capital C. So take about 5 minutes. We'll walk around and work on those. Go. Oh, sorry. I never gave you the trig. So let me just give you the trig ones. Here we go. Okay, natural log of x. Is there anything more that after that? Okay, so here are some rules that we're not going to derive. If you want to sit down and derive those in the office hours, love to do it. But we don't have time to derive all the rules that you're going to have to memorize. So we're going to give you the trig ones. Sine, cosine, tangent, derivatives are. Derivative of sine is cosine. Derivative of cosine is negative sine of x. The derivative of tangent x is secant squared, etc. So we've got the other three. And then the derivative of natural log of x is 1 over x. Or x to the minus 1 if you want. Okay, log base b of x is 1 over x, and then also in the denominator, natural log of b. Now, do you have everything to do the screen? Times. Okay. Now do you have everything you need? Okay, let's just take questions on those so far. So, in all these cases, we have an exterior function g and an interior function f. Okay, so this first one, the exterior function is cosine. So we're going to take the rate of change of the exterior with respect to the interior, meaning leave the interior function as it is. Don't take the rate of change of that one. So we're going to do the rate of change of cosine, which is negative sine, with respect to the interior function as it is. That's what it says right there. Rate of change of g with respect to f times the rate of change of f, which is the rate of change of natural log is 1 over x. Okay? So I'm taking the outside-in approach, outside in, starting with the exterior function, and then multiplying by the rate of change of the interior, like I've written the formula in the top. Questions on the first one? So the next one, what's our g function? Is the exterior function. It's log base 5 of sine x. The interior function, sine x. So we're going to do the rate of change of log base 5 with respect to its interior. So that's going to be 1 over sine x natural log of 5, according to what I showed you there, times the rate of change of the interior, cosine x. Questions on that one? Okay, here, what's the exterior function of this one? Something squared, right? So the g function is something squared. So I'm going to do the rate of change of g, which is 2 to the first, but with respect to the interior function as it is. Don't change it. Then you multiply by the rate of change of the interior function, which is our 1 over 2 radical x. Rate of change of e cubed, not 3e squared. Watch out. That's a number. E cubed is just a constant. So the rate of change is 0. Okay, this one is actually has a constant multiple tacked onto it, so we're going to just hold on to the constant, right? So 6 times, what is our g function? 7 to the something. So the rate of change of g with respect to that something is going to be our 7 to the something times natural log of 7. So we worked that out last class, what the rate of change of a to the x was. But then it's chain rule. You've got this interior function, so we need to multiply by the rate of change of the interior function. Questions on these first 4? Especially if you've never done these before this semester. Is this making sense? Okay, so this last one now. Overall structure of this. What's the overall structure? Something to the 1/2, right? Something to the 1/2. So we can think of our overall g function to the 1/2. Therefore, the rate of change will be 1 over 2 times the square root of the rate of change of this, or just this as it is? Okay, with respect to f, not the rate of change of f. So we're just going to rewrite that 6 times. Okay, but then times what? Times the rate of change of that, the interior, right? What's the structure of the interior? Sum or difference. We have the difference of 2 things. And we know that's our really easy rule, where we just take the rate of change of the first minus the rate of change of the second. What's the rate of change of the first? Right, so we've got the chain rule inside of the chain rule. So when we come to the rate of change of 6 times 7 to the tan x, we're going to follow all the rules. We already did that one. So we could do it again, or we could just write it down. Right, so this is now the rate of change of 6 times 7 to the tan x. So we're going to just write it down. So now, when I get to this rate of change of the interior function, it's the chain rule. So I got to follow the chain rule. Okay, minus the rate of change of cosine natural log of x. Again, we already did it. So it's minus a minus, so I'll make it plus, okay? I'll do that. Plus sine of ln of x. I'm going to change it back. So minus. We see exactly what happened. So what happens? These rules come in combination. We have the chain rule and the big picture of that, of the square root with an interior function, but that interior function uses this chain rule. So this whole thing is that rate of change function for that last square root function. Okay, so if I lost you, ask. Because they're going to get a lot worse than this. You don't want to keep up all the way as we get to the hard ones. So if I lost you on this last one, can you ask a question? Yes, please. It'll be the rate of change of this minus the rate of change of this. And what was the rate of change of cosine natural log? It was negative sign. So I'm just leaving it as minus minus. At first I thought I would just do plus, but I changed my mind. But yes, if you simplify this, you just get plus. Yeah. Other questions on this example? Yes, please.
For the 6 times 7 tan x.
Right.
And the first one, why did you put ln of 7 after?
Okay, because what is the g function? The g function is a to the x. And what's the rate of change of a to the x? Okay. No, it's the rate of change of g. G of x is 7 to the x. So what is the rate of change of g? Yeah, always. So we're doing the rate of change of g, so that will always have that ln of 7. Now our interior, instead of x, we have tangent x. So you got the rest of it. Okay. Please ask. Other questions? Don't hesitate. Yes, please. Yeah. Right. Yep. So this could also be written as 1/2 times this argument to the negative 1/2. That's exactly the same thing. If you want to do it that way, it's okay. Both are equal. So this is the same as 1/2 times this interior thing to the negative 1/2. Exact same thing. But then this is non-negotiable. You had to have it just like that. Good questions. Any more? All right, so that's a pretty good treatment of the chain rule. So let's talk about if a function is the product of two functions. So what we haven't dealt with yet is product or quotients of functions. So here's two easy ones. Sine x. What's the derivative of sine x, or the rate of change function for sine x? Cosine x. Rate of change or derivative of e to the x. So that's a very special function where values of the rate of change are the same as the amount, or the amount of accumulation at every value x. Okay? Watch out, it's not x e to the x minus 1. Okay, watch out for that. It's not x e to the x minus 1. When the x is in the exponent, it's an exponential function. All right, so suppose that k is the product of these two. And so is the rate of change of k equal to the rate of change of f times the rate of change of g? Kind of like the sum function, right? We know that if we had a sum, we just take the individual rates and add them together. So can we take the individual rates and multiply them together? So thousands upon thousands of calculus students have tried to do this. It would be nice, but it's not true. Okay? It would be really nice, but it's not true. So when you have the product of functions, you can't take the rate of change of the first times the rate of change of the second. Doesn't work. What about quotient? Again, wouldn't it be nice to take the quotient of the rate of change functions? We can't. Okay, so that only works, that kind of approach only works with sum and difference. When it comes to product and quotient, it's a different animal. Got to do something else. All right, so don't try to, I'm going to show you the derivation of the product rule. Don't try to write this down and go fast. If you're interested, you can slow the video later. Okay, so, but let's do the first step. So I've got this function f times g of x. and I'm trying to write the rate of change of f times g of x. So how, if I don't know what it is, how would I start? What would I start with? The rate of change of f times g of x is equal to what? How would I start? How would I start? We should all know this. Yes, ma'am. Okay, what is the trusted form for f times g of x? Okay. Okay, so we don't, okay, yeah, that's true. So, yeah, keep going. Okay, right. So the trusted form would be f of x plus h times g of x plus h minus f of x g of x over h. Right? That's our change in y for our given function over a change in x of h. Okay, so what we do to figure out what this, so again, we're going to do some work on this to try to figure out what this equals. And so here's what we do. Again, I'll go fast, don't try to write this down, just listen. We're going to do this thing, we're going to subtract f of x times g of x plus h and add f of x times g of x plus h. And so that's essentially adding 0 to the numerator, so it's still equal to what we had before. You see that? So I'm adding and subtracting the same value, which doesn't change the value of the quotient. Okay, and you say, why do you do that? Why do you do that? Well, because it works. Okay, it works. Watch what happens. So now I can gather together the first two terms, and I'm going to gather together the second two terms. And in the first two terms, notice I can factor out what? G of x plus h. And in the second two terms, I can factor out an f of x. So I'm gathering those first two terms together, factoring out g of x plus h, gathering the second two terms together, and factoring out f of x. And when I do that, notice what I have. I get g of x plus h times this. And then I get f of x times this. Do you recognize what I circled in black? What did I circle in black? What is that? F of x plus h minus f of x over h. That's the derivative of f, or the rate of change of f. And then what I circled in blue? That's the rate of change of g, or the derivative of g. So what we get is, we get g of x plus h times the derivative of f, plus f of x times the derivative of g. And so when we let h get really small, that g of x plus h just becomes g of x. F of x is f of x, and so here's what we get. We get g times the rate of change of f plus f times the rate of change of g. And then this is just those switched around. The blue, just those two switched around. So it's not the derivative of f times the derivative of g. It's this formula instead. So you could say the first function times the derivative of the second plus the second function times the derivative of the first. And that gives us the rate of change of a product of functions. Questions on that derivation? Okay, let's try an example. Okay, so this is just repeating what I just said. The rate of change of a product is the first function times the rate of change of the second plus the second times the rate of change of the first. This is really hard to mess up because addition is commutative, addition can switch, and each multiplication can switch. So you just got to remember that you're multiplying one function times the rate of change of the other, and then you do that both ways and add them. Okay? All right, so what did we say? We identify the structure first. I've got f of x equals 2x to the fourth minus 3 times 3x squared plus 7 what is the structure of the function f? What is that in the big picture? Is it something to a power? Is it the chain rule? Is it a composite function? What is it? Product. It's the product of two functions. If you blur your eyes and stand way far back, it's a product of two things. Therefore, the rate of change. So identify structure first. It's the product of two functions. We'll call the first one g, and we'll call the second one h. And so therefore, what will the derivative or the rate of change of f be if I call that first one g and the second one h? So based on the product rule that we just derived, it'll be the first times the derivative of the second plus the second times the derivative of the first, or g times h prime plus h times g prime. So now we just got to figure out what each of those four things are, and we assemble it. We're done. What is g? Well, we already know what g is. It's just what we said it was, right? That's g. What's h? H is just that. So all we have left to figure out is what's h prime, or what's the rate of change of h. And that's an easy one. 3x squared plus 7. Rate of change is 6x. 3 times 2x. And what's the rate of change of g? 8x cubed. So there they are. And so we've got all the pieces, and we just assemble it. Done. So we just applied the product rule. The first times the derivative of the second plus the second times the derivative of the first. Okay, here's the deal. So that big list of 150 problems, the rest of those, you've done some of them. Now all the rest are going to be due Monday. So you've got, and you can do lots of them now. You've got the chain rule and you've got the product rule. Find the ones you can do and get started. They're all due Monday.